So let's talk about what exactly happens when an electron, or when a molecule absorbs a photon. And we're going to be thinking mostly about electronic transitions, so things that you would see in the UV visible range. So light matter, magic. So let's find out what's behind the curtain of this magic. So we've talked about these different ways that light can impact molecules, and they're listed in order of increasing energy required to generate those kinds of transitions. So let's move right along and talk about what can happen. We're going to be thinking mostly about the UV-Vis electronic transitions. So let's go through this diagram. It's called the Jablonski diagram. And here you have your ground state, S0. And these purple lines are meant to represent vibrationally and rotationally excited ground states. So S1 is an excited state singlet, where you would most likely excite a molecule or an electron if a molecule absorbs a photon. And then these purple lines again represent vibrationally and rotationally excited states within this excited state singlet. So basically you have excitation, and then you can have non-radiative decay to the ground state of this S1. So that's vibrational and rotational energy that's lost. So then once you get to this ground state of the excited state singlet, then you would have the emission of a fluorescence photon. So you would eject a photon from the molecule and go back to the ground. The electron goes back to the ground state. Okay, and that's called a fluorescence event. So then there's some other options as well. You can undergo non-radiative decay to the ground state of the excited state singlet, and then undergo internal conversion to an excited, vibrationally and rotationally excited state of the ground state, and then undergo non-radiative decay back to the ground state, the unexcited ground state, S0. A third option is that you can undergo intersystem crossing to an excited state triplet, and then a non-radiative decay down to the ground state of the excited state triplet. And then if you have emission of a photon at that point, then you would have that's a phosphorescence event. You can also have intersystem crossing again, and then over to a vibrationally or rotationally excited ground state, and then undergo non-radiative decay back to the ground state. So these are all possibilities, and this is what gives rise to fluorescence and phosphorescence, and so this is just sort of the terminology that you need to know. Alright, so we've talked about excitation, where you go from the ground state to the excited state singlet, and that can be a vibrationally so this star is going to mean not the ground state of the excited state singlet, but some energy level above that, rotationally and vibrationally excited. So you can have non-radiative decay, where you go from that excited state down to the ground state of the excited state triplet, or something similar. There were a bunch of non-radiative decay events shown on the last slide. You can also then undergo internal conversion, where you go from the ground state of the excited state singlet to a vibrationally or to an excited state of the ground state. So then you can also undergo intersystem crossing, where you're going from the excited state singlet to an excited state triplet state. And from there, so when you have photons emitted from either the excited state singlet or the excited state triplet, you would have fluorescence or phosphorescence. And the cool thing about those, the difference between these is, well, I mean, for one thing, the transition that's occurring, but also the time scale. Fluorescence occurs on a very short time scale, from 10 to the negative 8 to times 10 to the negative 4 seconds. But phosphorescence can take much longer, up to 10 to the 2 seconds. And so you can see some very cool Like that's why things glow in the dark, because you have fluorescence. So let's talk not about absorption, but about the emission events. So luminescence is basically the emission of photons from an excited state molecule that's returning to its ground state. So these examples of luminescence are the fluorescence and phosphorescence. And this is much more sensitive than absorption. And your book gives a really, I think, a very good analogy, where if you have, a whole football stadium full of people holding candles, and 500 of them, blow out their candle, you're going to have, you're not going to be able to detect that difference nearly as well as if you have a totally dark stadium and then 500 people light up candles. You're going to see that as a much larger change. So that's what we're talking about when we're talking about measuring the luminescence. So basically, you have the excitation that we've talked about before to the excited state singlet, and then you have the emission. And the reason that there's an energy difference in the energy that's absorbed and the energy that's emitted is because of non-radiative decay. And so you're going to non-radiative decay down to the ground state of the excited state singlet, and then again you could potentially emit a photon that leaves the electron in an excited state, or in the molecule in a little bit of an excited state, even when it's in the ground state, so that it needs to relax farther via